PhD students at the University of British Columbia in Vancouver, Roland Bauerschmidt and Jesse Goodman. And I'll turn it over to you now.
So I hope everybody has an exercise sheet. So our plan for this exercise session is to have you work on most of the exercises yourself for a little bit, since most of the problems should actually be very elementary, and so we'd like to give you some time to work on the problems and then go through the solutions together. Maybe before starting, I recall the very basic definition of this morning. What is a self-avoiding walk? A self-avoiding walk is a path on the d-dimensional integer lattice. You could take any graph if you wanted to, but we'll only look at the d-dimensional hypercubic lattice in this TA. And we'll also mostly consider the nearest neighbor step distribution. If you recall this morning, we've also looked at walks taking steps, more general step distribution, but for now, so omega, the set of steps will be the edges in ZD was unit length. And so Cn denotes the number of self-avoiding walks with starting at 0, any endpoint. So and we've seen earlier that Cn is a submultiplicative sequence. And not only in the previous tutorial or in this morning's lecture, but also in the previous, in many of the previous lectures, we've appealed to the sub-additivity lemma. And so the first thing we'd like to do is give you some time to prove this lemma and then go through the proof together. Oh, maybe I should write down what the lemma is for those that don't have exercise sheets. So
So we'll give a couple minutes for you to work on this. Feel free to work with your neighbors or whatever you like, and we'll be circulating around. So if you have questions, you can ask us.
Sn.
yes.
So m and m are the same? Or?
Oh, no, yeah. Sorry. It's a typo. So obviously it suffices to show that if we modify the statement a little bit, we replace a limb by a limb soup. That doesn't change anything. And we remove the inf. We want to show that this is larger than an over, let's put an m here, for all m. And the idea is that we write n as a multiple of m with a remainder. So we fix m, we write n as k times m plus a remainder, which lies between, so r. So like this. Can make use of subadditivity to rewrite this a index n as k times a index m plus ar. This just follows by repeatedly applying the subadditivity property. This is the same as k times mk plus r am plus 1 over mk plus r ar. And so ar can only take finitely many values. So as we pass to the limit as n tends to infinity, this will go to 0, and sorry about that. And this quotient will go to 1 over m, which shows the statement. So, what? So this allows us to define the connective constant that had already been defined in the lecture as log of the limit of Cn of the sequence log Cn divided by n. This is a limit. I'm sorry. Log of mu, yes. And in the lecture, we had already seen lower and upper bounds that hold in any dimension. And the next exercise is to improve these bounds to strict bounds. So in the exercise, in the lecture this morning, we've seen that mu is strictly between, between 2 and 3 in d equals 2, and the following exercise is to improve these bounds to strict bounds.
I'll comment that this exercise can be effectively solved by drawing, well, with a tiny bit of explanation, from 2 pictures. So if you can get 2 expressive pictures, you'll be done.
And we take suggestions for how to do this. So if you have an idea how to do this, please raise your hand. And okay, so let me recall that we obtained the upper and lower bounds on Cn, the number of self-avoiding walks with n steps, by restricting to a subclass of self-avoiding walks for the lower bound, and restricting to a superclass of walks to a class of walks which include the self-avoiding walks to obtain the upper bound. So how did we obtain, say, the lower bound? The number of self-avoiding walks is clearly less than the number of walks which only increase in every direction. So say walk like this. So the components of the walk increase in every direction as time goes, as we increase n. So this gives a bound which is
other side.
This way around. So this gives a bound d to the n. In passing taking the n square root and passing to the limit, this will give us the lower bound 2 in 2 dimensions. How can we improve this bound in, say in two dimensions? Exactly. So the idea is that you can also, if you do something like this, so you maybe let me use a different color. So if you consider walks that either increase in every direction or that make little half loops like this and then increase in every direction or make more of these half loops, then this walk will clearly be still self-avoiding. So for example, we'd obtain that C4n is greater than d to the 4 plus 1 to the power n, and taking the 4 to the n square root of this expression, taking limit n to infinity, improves this bound to a strict bound. And for the lower bound, we can obviously do something similar. What we did in class is we considered walks which do not reverse its previous steps. So we considered all walks which did not necessarily have to be self-avoiding, but which would never make a step back. So this would not happen, that a walk would step from this point to this point and then step back and go on. And we can clearly allow more general patterns of what the walks cannot do. So for example, we can exclude a little loop like this. So we could exclude walks to do loops like this, and then we'd get a better bound than 3. So the third problem is to show that self-avoiding walks is not a stochastic process. So consider a family of probability measures on n-step self-avoiding walks, which we denote by Pn. such a family is a consistent family of measures if the projections to walks with fewer steps coincide with the measure at this length of steps. So that means that, so for rho, a walk with, so say rho is in Sn, a self-avoiding walk with n steps. The probability under the measure Pn is the same as summing over all walks that extend this walk rho, meaning that it coincides with the walk rho for the first n steps, but then could be different. So we denote this by writing omega is greater than rho. Taking the measure of these, average over these walks. So this property means that Pn is consistent. So can anybody give me an argument why self-avoiding walks are not consistent? Sorry? Exactly. We can have walks which, let me see if I can draw this now. So this is a walk which is self-avoiding, but it gets trapped at this point. So there's no walks that extend this walk. So clearly this cannot hold, because if I may recall, Pn is the uniform measure on all self-avoiding walks. I guess I didn't say this, but it's in the statement of the problem that the self-avoiding walk is a uniform measure on self-avoiding walks of fixed length. So under this measure, this family of measures is not consistent. So the fourth problem deals with the strictly self-avoiding walk in one dimension. As has been mentioned in the lecture, it's a kind of a, well, it's a very, it is trivial. There's nothing to be said really, because it either goes left or it goes right. I guess we're doing the exercise to recall the definition of the two-point function, and so the exercise is to calculate the two-point function of the strictly self-avoiding walk in one dimension, which should be very easy.
I'll also comment that I'm told this question is maybe not quite as easy as it seems, because there's been correspondence from a noted mathematician who apparently got a different answer than the one presented here. So be on your guard.
So in fact, we're interested in the Fourier transform of the two-point function. So the Fourier transform of the two-point function is defined as the sum over all points in ZD of the two-point function valued at x times e to the ik x. So okay, this is a calculation. We call that the two-point function gz of x is defined as, the definition is still there. It's the number of self-avoiding walks starting at 0, ending at x that takes n steps, summed over all positive or non-negative integers n times z to the n. In the case of the self-avoiding walk in one dimension, Cn of x is very explicit. So what can it be? It's 1 if x has the length n, and it's so this is and it's 0 else. Can I write bigger? Oh, okay. It's actually, what? Oh. So plugging this in, we obtain z to the x. Taking the sum over all x, weighted by e to the ikx, we can split this into, this will be a sum over x, which is all integers. We can split it into a sum over positive integers and over negative integers. So what we obtain is sum over all n greater or equal than 0, e to the I k n times z to the n plus the sum over all negative integers e to the I k n z to the minus n, and we can rewrite this as the sum over all positive or non-negative integers as follows. And then we need to subtract 1 since we've counted 0 twice. And these are geometric series which converge for z less than 1, and they're equal to 1 over 1 minus 2. Well, and if you plug in everything, you get a formula. Is there anything wrong here? Okay. So I'm not sure if I should write down this formula now, since I would probably make a mistake in the calculation.
There'd be a good precedent.
Sorry?
There'd be a good precedent, we hear.
In the next exercise, yes? So actually I'm actually not so sure myself why I'd be interested in the Fourier transform of the one-dimensional self-avoiding walk. I think it's just an exercise to to get comfortable with the notion of the two-point function of the self-voiding walk. There's. Oh. Well, it's a generating function for this sequence of numbers, right? We're very interested in this sequence of numbers, but this sequence of numbers itself is, we don't really have many techniques to study the sequence of numbers. And taking the generating function is something we can do and which we can work with much better, at least for many aspects, I think. I don't know, Gord, do you have anything to add?
On Thursday, you're going to see plenty of Fourier transforms of two-point functions. So you just have to wait.
So this actually brings us right to the next exercise, where we look at kind of the, well, we're considering a generating function to be given with certain estimates, and we'd like to conclude certain estimates for the coefficients of this generating function. This is, as Gord has mentioned in the lectures, is a Tauberian theorem, and it, in this case, requires very good control of the generating function that's given. So this is problem number 5. Could you turn down the volume a little bit, maybe, because I think it's. Could you turn down the volume a bit? Or is it? Is it too loud? Thanks. So we assume that in, can you still hear me? Is it, no? Okay. So we assume an analytic function to be given with a radius of convergence 1. And we assume that we have an estimate for f that's valid inside in the interior of the whole unit disk in the complex plane, namely that f of z is in absolute value is less or equal than a constant times 1 minus z to the minus b, where b is a constant greater or equal to 1. So this is kind of a, this function blows up as z approaches 1. And under this assumption, we can conclude that the coefficients an will grow at most like c, which is another constant, times n to the power b minus 1 if b is greater than 1. Or like a log of n if b is equal to 1. And well, the key idea here is to make use of the Cauchy integral formula for the coefficients of this analytic function and estimate the integrand using the estimate given.
I'd comment here that if the inequality was actually an equality and you removed those absolute value signs, then this would be more or less, you'd have more or less an implication to an equal sign as well. The only slight difference would be in the b equals 1 case, where you would not get that logarithmic term. So that logarithmic term will sort of come out of our not quite perfect knowledge about the function f.
Yes?
Sure. So if this written big enough? If you actually had an equality here, f of z equals constant 1 minus z to the power minus b. And here we could even get, we could even divide by zc here if we wanted to move the singularity to a different point. Then we could, well, now this is an explicit function and we just have to recover its generating function coefficients. So if I look at the corresponding an, an would have the form constant. We'd have a zc to the power of, sorry, it's either plus or minus n. It would be minus n. And then we would have n to the power b minus 1 and possibly some lower order corrections depending. But in any case, we'd have certainly an asymptotic equivalence. So this is one of the reasons that the asymptotics that Gord was presenting this morning, where we had this mysterious constant mu, the connective constant, and then some rather sort of arbitrary-looking polynomial type correction, is actually not so unreasonable. It's just signifying that the generating function has as its dominant singularity something that's of the form 1 minus z over a constant to a power.
Okay, since not so much time is left, maybe we should go ahead with the solution. As suggested on the exercise sheet, we're looking at the contour. This is a complex plane, and we're looking at the contour with radius 1 minus 1 over n to evaluate the nth coefficient an. And one reason why we're doing this can also be seen in the following, in the formula for the coefficient an. So we have an estimate for f. So adding absolute value signs will give us an estimate as follows. And what we'd like to do is we'd like to take this factor out in front of the integral. And evaluating on this contour, it will be bounded by constant that's independent of n. So if we write absolute value of z to be 1 minus 1 over n, we have that z times the absolute value of z to the power n plus 1 is equal to 1 minus 1 over n to the power n plus 1. And this is bounded below by, so this tends to the exponential, e to the minus 1. So this will clearly be bounded by a constant times e to the minus 1. So we can take this constant out front and are left with the integral over f of z dz. And so we need to evaluate the absolute value of 1 minus z to the power b minus b on this contour, and this will give us a formula. Maybe I'll just write down the result since it's well, okay. So we evaluate it by taking the real and imaginary parts separately, which would be bigger than the absolute value of f, and take this to the power minus b. And so the only problem is will be near the singularity 1. So if we restrict, so we'll be able to restrict to this arc of the integral, which contains the problem because the function f is bounded away from 0, is bounded above on any set away from 1 in particular on this arc. So this will merely contribute a constant. So the imaginary part of f of z is bounded by, we recall that.
Roland, I think here you're actually looking already at 1 minus z, which we've used to bound f. That's why we've got the minus b already.
Well, what I'm looking at is e to the I phi So if we're looking at the imaginary part of this, yes, I'm actually looking at the imaginary real part of this. I'm sorry. So the imaginary part of this is equal to which is larger than 1 over n. And the real part is by using estimates like that the sine function is strictly concave, and we can bound it on the interval from 0 to pi over 2, but by a linear function.
When did you use the hypothesis? I'm confused. You've got the minus b in the first line. Do you want it?
In this line?
Yeah.
Yes, I've estimated f by, this is, okay, I'm sorry, yes, this line is confusing. This is evaluating the function of the contour using the hypothesis. So this is the same as we have here, and then we can estimate the real and imaginary parts and get an estimate. Say, looking at the part from 0 to pi over 2, get an estimate of like 1 over n plus and we only deal with this part since the rest will be more of the same. Using a substitution, this is the same as 1 over n. So we substitute say theta equal to 1 over n plus 1 minus 1 over n e to the using these estimates here. So yeah, I should write this down. So I actually want to look at this. So this part is less than this. And we obtain a constant out front, which and theta to the minus b d theta. Plug in phi is equal to pi over 2. These will just cancel. We get 1 minus. We get 1 over n plus 1 minus 1 over n, which is just 1. And if this integral is evaluated, you obtain 1 over 1 over n times a constant which will depend on b, and you will obtain 1 over n to the power b plus 1 minus b plus 1 minus 1. And this is the estimate that we have desired, since this is less than or equal than c to the n to the b minus 1. And it's similar for the other intervals.
One comment about this method is how we knew in advance that we should choose the contour where z was about 1 over n away from 1. Just as a general sort of remark, when you're extracting these coefficients, generally, when you're extracting these coefficients using contour integrals, what you want to have happen is that your contour, the main part of your contour, and for us, the main part of the contour was this little section right around 1 where the function was blowing up. You want that part to be at a critical point for your integrand. Without going particularly into details of why exactly you want that, essentially you want to sort of minimax or max-min argument. So I want to find a point where d by dz of f of z over z to the n plus 1 would equal 0. Now, in the case where we had our estimate of, again, I suppose that my function was actually exactly equal to the bound I was given, that it was 1 minus z to the minus b. What you do when you work this out would be you'd find that z is actually not exactly equal to, but approximately 1 minus 1 over n would correspond to the critical point, and that's the best place to try and evaluate to have your contour go through.
And at the very end, we'd like to briefly give one of the reasons why the self-avoiding walk is tractable in high dimensions, not tractable in low dimensions. And that is because typically two random walks will intersect themselves with, so we'll calculate the expectations that two independent self-avoiding walks will intersect themselves. This expectation is the expectation of the number of self-intersections of two independent random walks will be infinite in low dimensions and will be finite in dimensions 4 and higher. More than 4. So
the picture, maybe I'll just draw the picture that corresponds to this. We want to know if we've got a walk that's likely to be self-avoiding. So let me draw one side of the walk and the other side of the walk. Well, if they didn't intersect much, then maybe they'll be self-avoiding. And if they intersected a lot, they probably wouldn't have been. This part probably wouldn't look like a self-avoiding curve. This isn't a proof, of course. This is just a picture.
So problem number 6 is an exercise that that I assume that most people have probably seen before. It's the relation between. So maybe let me write it down, but not say too much about it. So problem number 6 states the following. So given a simple random walk xn, part A says. So if we denote by u the probability that a walk ever returns to the origin, so say a random walk, so this is standard random walk now, that a walk started at 0, ever returns to the origin, and if we denote by n the random number of visits to the origin. So this includes the first visit at time 0. And by m, the expected number of these visits, then there's a relation between u and m, namely that that m is 1 minus u inverse. So in particular, if the walk is recurrent, the expected number of self-intersections, the expected number of visits to the origin will be infinite, and otherwise it will be finite. And I think we can probably skip this exercise. It's a straightforward application of the strong Markov property, but I would probably introduce more errors if I did the calculation on the board now. Then it would do benefit. What I'd like to take a look at, though, is how we can express m, the expected number of visits to the origin, in terms of the Fourier transform of the step distribution. Let me briefly recall that. Actually, I'm not sure if this has been introduced so far, but we will generally denote by d the one-step distribution of a walk. So d of x is equal to, so for the nearest neighbor model, d of x is equal to 2d inverse times the indicator function that the one norm of x is equal to 1. And we will denote the Fourier transform by d hat of k, which is and in the case of the nearest neighbor models, this is a very explicit calculation to see what this is. We just plug in this distribution, then we see that this is the same as 1 over d, the sum cosine ki, where so ki is the ith component of the vector k. And problem B is to show that m, the expected number of visits to the origin, can be expressed as the integral of 1 over 1 minus d hat of k integrated over the torus, d-dimensional torus. In particular, it will be finite if this function 1 over 1 minus d hat of k is integrable, and if and only if this function is integrable. And this will actually, so when Gordon will introduce the lace expansion, we will see a similar expression for the self-avoiding walk that contains an extra term, which will account for the self-avoidance the walk has to satisfy. And so this is an instructive exercise to recall this relation. So noting that this probability that at time n the walk is at 0 is the same as the one-step distribution convoluted n times with itself evaluated at 0. This is the definition of the simple random walk. Can be expressed in terms of the Fourier transform of the one-step distribution. Essentially, this statement amounts to summing over this expression d hat of k to the n, and realizing that this is a geometric sum. There's one subtlety in doing this, because the best uniform upper bound on d hat of k is 1. So we will not be able to apply the dominated convergence theorem directly to see that the sum and the integration can be exchanged. But it's easy to get around this by say inserting before taking the sum. So we'd like to take the sum over n, and if we put a t to the n on both sides first, where t is less than 1, we'll be able to do this. And this is the monotone limit, so we can take the limit as t goes to 1 from below, and these expressions, and then for these expressions we'll be able to use the dominated convergence theorem again. Maybe I'll skip this because it's because I briefly like to mention the 7th exercise before finishing. The 7th exercise is kind of a similar flavor. We consider two independent random walks, xn1, xn2, which are independent simple random walks. We consider I, which is the number of times these two walks intersect each other, which is the sum over ij greater or equal to 0, indicator that x1 I is equal to x2j. And we note that the expectation of I can be expressed in terms of the integral 1 over 1 minus d hat of k as before squared dk. I guess it's a 2 pi over d here. And it can be seen very similarly to before. And I guess the take-home message from this calculation is that this expression is the same as 1 over d, well, I guess 2d k squared plus higher order terms. And that the integral of k to the minus p, say over minus epsilon epsilon to the d, exists if and only if d is greater than p. And so from this calculation, we see that, so in the simple random walk is recurrent in dimensions 2 or lower and is transient in dimension 3 and higher. And we see that two independent simple random walks have a finite expectation of self-intersections in dimensions above 4 and have below 4 and have an infinite number of expected self-intersections in dimensions above 4.
Other way around. Other way around there.
Other way around, sorry. But you know what I mean. So yeah, I guess we should probably finish. Or do you have any remarks?
So just at least heuristically, this 4 is the 4 that comes up as being the critical dimension for self-avoiding walk. This is the reason why some of the results, wherever we see d greater than or equal to 5, it's exactly coming from this d greater than 4 that we calculated right here.
Okay. Any questions?